which is global minimum, so x star. Okay. So x star is Q inverse B. Okay. So what happens, basically what happens is x star makes the gradient 0. Okay. So this is the problem we want to solve. And the conjugate gradient method converges at most n iterations for this. So now let's, last time we learned projections. So projection is in terms of subspace. So our motivation is steepest descent search along a line, but conjugate gradient search in the subspace. So that's a difference. And okay. So we define projection. First, S is a subspace. Then the projection of an arbitrary. So U is some element in Rn. Okay. The projection of U onto the subspace of S is defined in this way. That is, the inner product of U with V is the inner product of U with V is equal to its projections inner product with V. Okay. All right. So actually, we have a name for this. This is just the famous L2 projection. Okay. So then we define another projection. That is a Q projection. Let me write this smaller. This we have learned in even maybe in high school when we learned this plane geometry. Okay, and we learned it again in vector calculus. You know, when we learn inner product, we compute the projection, and now we learn it again to put it in an even higher perspective. So the Q projection. So if we add a superscript Q here, what we need to do is, this is Q inner product. Okay. So the definition are the same, except we have a Q here. So this is normally called Q projection, or even it got a more famous name. So it can be called the looking projection. So once the matrix Q is involved. Now let's put, so this is a projection in the perspective in optimization. So the definition of projection is, so let's draw a diagram. So the definition of projection is, so this is our S, this is like our U, and this is the projection of S of U. So here, the projection's distance to U, okay, is the minimum among all possible points V in S, V to U. So this is our projection. And if we think L2 projection, the projection of U to the original U's distance is the minimum among all possible V's in this subspace S. Okay. So similarly, so we proved last time, we proved last time for this, but let's just say we take granted that this is true as well. All right, so let's review. So the Q inner product is just X transpose Q1, okay? And XQ norm is X transpose QX1/2, and this Q has to be and symmetric, positive, definite matrix. Okay.
Excuse me, the V is kind of like be any arbitrary vector in the S-plane, right?
Yes. So V is something, if we want to draw, V can be this, can be this, can be anything on the S-plane. Yes, thank you. So now we want to put this projection into the perspective of optimization. So let's draw another diagram. So for example, maybe this is our, let's think about we're in the, 3D space. Okay. So this is our kth iteration. So now we are solving optimization problem. And first, before we do that, let's acknowledge an identity we learned. So this identity we used multiple times. Okay. So here's the thread of thought. We want to optimize this function. Okay. So for simplicity, we assume this function is a quadratic function. But in general, assuming convexity is fine. So we're assuming this function is convex. And we minimize this function. So then, this function subtract its minimum value. This is a constant, okay? So to minimize this function, it's equivalent to minimize this point's distance to the minimizer. Okay. So let me write this statement here. So to minimize f. So to minimize f, it's equivalent to minimize f subtract the constant. This is a constant. Okay. To minimize f, it is equivalent to minimize the q distance. So this is distance in the q norm, which is that. Okay. The q distance with the unique local minimizer we have, x star. All right. So maybe I'm drawing our S like this. Okay. So what happens is, maybe this is our x star. To put this projection into the perspective optimization is, if our current iterate xk is here, okay, we want to search our next iterate, maybe say such that the next iterate is has the minimum possible distance to this local minimizer, okay, among this search subspace. All right, so this is our goal. So the goal, so our goal is to search k plus 1's iteration such that x plus 1 iterations distance, q distance, is minimized. Q distance to x star is minimized among all v in S with xk plus 1 equals xk plus v. Okay, so we search in this subspace, and such that our next iterate, so this is our current iterate, we move in the search subspace. Okay, so we add a vector in the search subspace so that this guy's distance to this is minimized. Then now we draw the diagram. So this xk, then what happens is what we need, so this is what we want. Okay. So what we want is to find x k plus 1. Find xk plus 1. Such that xk plus 1, okay, this is xk plus 1, this vector is xk plus 1 subtract xk, is what? It's a projection of xk subtract this x star, which is our local minimizer. Wait a second. So this is a projection of this. So it's end subtract beginning, right? So this is end subtract beginning. Okay. So it's a projection of x star subtract xk. So this is what we want to put in the context of projection. All right. So the idea is the global minimization is equivalent to minimize this q distance. So now, originally the steepest descent or the gradient descent search the minimum along a line, which is negative gradient direction. So now what we do is we take advantage of this optimization. We build a subspace based on the iterations, and what happens is we search the minimum in the subspace. Then the natural question, now we use the definition of, use the definition of Q projection, okay? So now we just use the definition, right? Because this is a projection, we can use that formula, okay? We can use that formula to compute xk plus 1, which is k plus 1's iterate. Okay? So So right? We use the definition. So xk plus 1 subtract the kth iterate, which is a projection, right? So this is projection as superscript q of x star subtract the current iterate. Okay. All right. So let's continue here. And by definition, the projection of this guy against, which is inner product with V, is the same thing with without the V. Okay. But now we face, I mean, V, so if our, so this is like for V in this search subspace, okay? Now we face the difficulty. Think about this. This inner product, if this is known, this inner product can be computed. So then we want to compute this. And this becomes this. But x star is unknown. We want to find x star. Okay, the whole point of our algorithm is to find x star, but now x star is in our equation. Okay? So the whole point is to find x star, but to get the next iteration, we need to use x star. This doesn't make sense. Okay? So however, the good news is, once we use the definition of Q, so this is this, right? So Q is symmetric. So this equals what? This equals Qx transpose y, right? So this is nothing but Qxy, the regular L2 inner product. Okay? So this is Qx star subtract Qxk V without the Q, regular L2 inner product. We don't know x star, but we do know Q times x star. That is, Q times x star is B, because the gradient of f, so you can either see from here, or the gradient of f is basically Q times x subtract B. So this is Q times x star subtract B. At x star, Qx star is B. Okay? So this is B subtract Q times the kth iterate of B. Okay? Now, what is this? This is a residual. This is also the negative gradient. This is also the negative gradient at the kth iteration. Okay.
Oh.
So we start from here, and we ended up here. Okay. So now let's see. Now let's use this relation to derive things. Okay. So example 1. Okay. When our search space has dimension 1, our search subspace is the span of GK, and where GK is basically our notation for negative gradient or gradient. It doesn't matter. Once we talk in the context of a subspace, it doesn't matter. The signs doesn't matter because it can be plus or minus. Okay, so I think some textbook uses G as negative gradient. So I think here, I think in my notes I use positive. But it doesn't matter that much once we put it in the context of minimization. So, okay, so this is our thing. Now we use this formula. Okay, so we use this formula that is for any V in this subspace. We start from here, we ended up here, so that is xk plus 1, subtract xk v q norm, okay, equals what? Equals a negative gk. L2 norm. Okay. So because our search is like this one, okay? Because we search in the subspace of our next iterator, so then the difference of this is in S, so which means, so this implies equals, so let's say, let's let this to be alpha times gk. Okay, this is a dimension 1 subspace, right? So it has just one basis. So it means this guy, subtract that, we just let it be this. Okay. So now we just plug it in. So so in equation number 1, equation number A, let's say, because I named the panel using this number. So in A, let V equals GK. So this is a subspace of dimension 1. Its only basis we need to care about is GK, right? Okay. So it's, I mean, the only basis we care about is GK. Then what we have is alpha GK, V is GK, this is Q norm, sorry, this is Q inner product, equals negative GK inner product against GK itself. Okay. Because of the property of the inner product, Q inner product, we can pull out this alpha by the property of inner product. simply assume this is not zero. So if it is zero, we already hit the local minimizer. This GK is a gradient at kth iterate. If the gradient is zero, we are at the local minimizer. We can stop. So we divide this to the right. We have, this is negative. So hopefully this formula looks familiar to every one of us. Okay. So when we look at this formula, so their difference is alpha times gk. This is the same thing saying xk plus 1 is xk plus this guy. Okay. So alpha equals negative that thing, which means we should move in the direction of negative gk, and alpha is that, and that happens to be our step size of steepest descent. Okay. So this implies so if we define this whole thing, we have a negative sign, but let me just write this way. So if we plug in alpha, we get this. And this is steepest descent. Okay. Because this thing is gradient of f at k here. So now let's look at example 2. Okay. So when the search subspace has dimension 1, we recover steepest descent. Okay. So example 2 is when the search space is dimension n. So I mean, if we have a subspace in Rn that has dimension n, then this subspace has to be Rn. Okay. So this implies S is Rn itself. All right. So if our subspace has the same dimension with our bigger space, then we're already at the bigger space. Okay. So now let's look at this. We still, you know, our goal is this. And by the thing we already erased, okay. Yeah. By the thing we already erased, this is equivalent that x k plus 1's iteration subtract x star q norm is the minimum among in this search subspace. Okay. Yeah, maybe I shouldn't do this, right? Yeah, maybe this notation is not good. Okay. Let's see what I did. Okay, the minimum of y subtract x. So we search the minimum of y. So this is equivalent writing. That is, we search our next iterate in the subspace S. Okay. So y is like our next iterate. So y is like. So we can rewrite this as. Y is in x k iterate plus this s. Okay, what does this mean is y equals xk plus b for b in s. So basically we choose some vector, we choose a vector in this search subspace S, we add this vector to the k iterate. All right. So if we do this, S is Rn. Okay, so S is Rn. So S is Rn. Okay. So Y is in xk plus S. I mean, we add a vector to Rn, we still get Rn. Okay. So this is Rn as well. So which means when our search space has dimension, so this is because xk plus this S is Rn, is a whole space. Because S is our whole space. We add a vector to this whole space, we still get the whole space. So this is Y in Rn such that Y's distance to X star is minimized. Okay. But this is 0. Because X star is an element in Rn. So we find the minimum distance of a point of Rn to X stars, of course, it's 0. Okay? So this is 0. Okay. This is 0, which means what? Which means this is 0. So this means our next iteration, we will reach X star. Okay, so what does this tell us? Example 2 tells us, so when the search space, the search subspace has dimension n, okay, then the next iteration reaches the local minima. I mean, this looks like a trivial result. This also tells us So one of the trait of conjugate gradient we wrote in the first place, it converges to our local minimizer at most n steps or iterations, is guaranteed by this. Okay, so think about this. So our goal is to build a subspace. We can build a subspace one by one. So at first iteration, we have a dimension 1 subspace. At the second iteration, we have a dimension 2 subspace. At the third iteration, we have a dimension 3 subspace. Then at the nth iteration, if we have a dimension n subspace, the next iterate. Went up. Okay. So the most interesting case is when so when we have dimension k. K plus 1. So our then our index will be consistent. So, and we let our subspace S to be span of D vectors. Okay, sorry, of a vector of k plus 1 vectors, but we use D to represent them. So D0, D1, dot, 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 D superscript k. So these are the bases, and we require, so this is a set of bases of S. So they are linearly independent. So these directions are linearly independent. Moreover, we want to require the following condition. So this condition, we just put it here for simplicity of computation. But later on, we will learn how conjugate gradient uses a very clever way to impose this condition. So what we want is, if the bases have different indices, di, dj, then they are orthogonal. Moreover, it's Q orthogonal. So if I is not j. Okay. So this is our setting. Still, we have this formula. Okay. So this time we so this time we start from x sub 0. Because this subspace is like after k iterations, we have built a subspace of k plus 1, and then we find our next iterate k plus 1's iteration, but instead we start from xk. Let's start all over from x0. This is our initial guess. Okay. So again, this is an element in S. Okay. So this projection. So let's recall this picture. This is our search subspace. This is our kth iterate. We can think this as 0. Okay. So we move in the direction of this, and this is our x star. Yeah, maybe this is not the best image. X star subtract, so this is beginning, this is end. Yeah. Yes. Okay, sorry. Okay. So this segment is equal to projection of x star subtract our initial guess. All right. Basically, we search among a subspace. Now, this subspace has basis d0 to dk. So, our k plus 1's iterate subtract x, this is the initial guess, equal to a summation of coefficients from I to k alpha I times di. And we plug in the formula we obtained, we erased somewhere here, right? So what we have is this, subtract this. Okay, so this is a projection by definition. Sorry, I forgot to add a 2 here. Okay, my bad. So this is a projection of Q, projection, that is, okay, for any V, in this search subspace, this equal to x star subtract x0 V. Okay. And this Q inner product. We derived that this, when we put Q, this equals Qx star subtract x0V regular inner product. Okay. And then we have, this is a negative gradient at the initial step. So this is negative gradient at the initial step V. Okay. Without the Q. All right. So this equals this. So now we put this here. Okay. And we choose V to be D superscript J. So J is 1, 2, so J is 0, 1, 2, blah, blah, blah. Okay. So what we have is the summation I starts from 0 to k alpha I bi. Okay. V is j, so this is dj. All right. Q inner product equals a negative. It's still visible. Gradient, negative gradient at the 0 iteration dj. Okay. So this is our equation. So this is a matrix equation. So this is an equation we want to solve for this alpha I. Okay. We solve actually using the same method of this. Think about this. We expand the left. We have this is alpha 0 d0, okay, plus alpha 1 d1 plus alpha k dk inner product against dj equals negative the gradient at the first iteration inner product against dj. This is Q inner product, but the second one is L2 inner product. So by the linearity of inner product, we can further pull out this alpha 0, and what's left is d0, okay, inner product against dj, q norm plus dot 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 alpha k d superscript k inner product with dj q norm. Now let's look at our setting. So if we can find such a subspace of these nice orthogonal bases, okay, if we have superscript I and j are different, they are orthogonal, which means all of these will vanish except one term. That is when j agrees with the superscript. So this implies it's only one term left. That is alpha j, and alpha j is d superscript j q norm equals negative g of 0 inner product with d superscript j. All right, so now we've reached an expression. So this equals, so we divide this to the right. So we have this is xk plus once iterate is x0's iterate, subtract, okay. So the coefficient is, for example, the first iterate. So j is like from 0, 1, 2 till k. So for example, this is 0, 0, okay. Q, so this is our alpha 0. Okay. And then subtract dot dot dot, subtract, last one is dk. So we have this formula. So this is our alpha k. And this whole thing is this summation of alpha I times d superscript I from 0 to k. Okay. So this is like the solution. This is the solution when we have this k plus 1 dimension subspace. Okay. So then, okay, I know like everyone is confusing. Okay, so what if we don't have? The answer is we always have this d. So when we have a subspace of certain dimension, we can always run this Gram-Schmidt. We learned in linear algebra, we orthogonalize vector, right? So we have first vector, then a second vector comes, okay? We orthogonalize this vector with the first vector. Then a third vector comes, right? Then we orthogonalize the third vector with the first two. But the bad news is Gram-Schmidt is not very efficient. So I won't go into detail in that, but so practically everything you guys learned in the first linear algebra class is not efficient. For example, computing determinant, something like that. So we want to build an efficient algorithm. Okay. So now the question is, so how to build the basis, orthogonal basis for the search subjects. So we have step one. So if we have a candidate for the direction, and we already know the candidate for this direction, okay? So that is our negative gradient, all right? So we ask a simpler question. So let's say, okay? So we ask a simpler question, okay? Let's say it's Q prime. So how to build Sk plus 1 from Sk. Okay. So this has dimension. So this one has dimension k plus 1, and this one has dimension k. All right. So we have two steps. Step 1. Find a candidate. Okay. So find the direction. And we already know it's our negative gradient. Okay. Find the direction and make it Q orthogonal to all previous directions. All right. And by making it Q orthogonal to all previous dk, d0 to dk vector, we name it dk minus 1. And we name it dk. Okay. So this is like the technical term. right here. So suppose, so now what we do is suppose, so now procedure is suppose we already have, k vectors, and they are orthogonal. So and we solve the formula, right? So we have just solved the formula to do that. Okay. So then we have our xk. So by, let's say, let's name this formula let's name this formula conjugate. So C. By C, the kth iterate is equal to, we start from x0, and we have this is plus alpha 0 d0 plus up until alpha k minus 1 dk minus 1. Okay. So then we obtain our kth iterate. Okay, so then we can compute. The gradient at the kth iterate. Okay, so which we denoted by g superscript k. So this is our sk that has dimension span. So sk is the span of that. Okay. Then what happens is sk plus 1 is the span of what? We have all previous k vectors, d0 to d superscript k minus 1. Okay. We add the negative gradient to it. But this is not Q orthogonal with all previous direction. All we do, we make it happen, Grand Schmidt. Okay. So that it's the same subspace, but we want to apply Grand Schmidt to these k plus 1 vector so that they are orthogonal. Okay? So, I mean, it's that simple. So this is like a practical application of Gram-Schmidt we learned back in linear algebra. So how to do Gram-Schmidt? How to do Gram-Schmidt is this is a vector. This is still a vector in this subspace, right? So what we can do is we can write, this. So this is a vector still in this subspace. Okay. So this is the subspace with basis we know. What we can do is we simply write the k plus 1 vector equals, okay, so beta times, beta times negative that, so we have minus beta times gk plus, should I use alpha? Oh, I use gamma. Okay. So gamma 0 d0 plus dot 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 gamma k plus 1 dk plus 1. Now what we do is we place the Q inner product to all of these. Okay. So think about this. We know this is Q orthogonal to this. Okay, so now let's see what happens when we place the Q inner product against the first vector. So keep in mind, our goal is to make this vector Q orthogonal to all previous vectors. So what happens is we make it so here. So now this is minus beta g k. Okay. D0 q. All right. Right? And then we plus this D0 Q inner product with this. That is gamma 0 D0 inner product with D0. Okay. And then plus dot 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 gamma k minus 1 dk minus 1 q inner product with d0. And we want to set this to be 0. We set this to be 0. And let's see what happens. Okay? This term, we cannot assume it to be 0. All right. This term is D0 Q inner product with itself. It's not 0, right? And all the rest terms are 0. So, for example, this is 0. If k minus 1 is not 0. Okay. So then we have, oh, wait a second. I think I want to inner product with, yeah, instead of the first one, we want to inner product with the last one. Yeah, let's do it again. Okay. Instead of erase it. So if we inner product with the previous one, okay, Q, so this equals minus beta G at the kth iteration against k minus 1 d Q inner product, and then we plus all the rest. Okay. So then we have this is gamma 0 d0 inner product against k minus 1 direction Q, and up until gamma k minus 1 dk minus 1 dk minus 1 Q. So these are zeros, so all previous terms are 0 except one term, and we set this to be 0.
Only this part is equal to 0, the whole or the whole?
The whole thing. So we want to set this part to be 0. So once we set this part to be 0, all previous parts are 0. This D0 inner product with dk minus y in the Q norm. So what we obtain is minus beta gk dk minus 1 Q norm, okay, plus gamma k minus 1 dk minus 1 inner product with itself in Q norm. So this equals 0. We have two constants here. Okay. We have two constants here. And what happens is we can just make it one constant. So we can absorb this constant to this. Okay. So we can just make it one constant. So this implies, so beta is basically what happens is beta is beta is set to this. And so I don't think I have time. So let's stop here. And once we choose this beta, we don't have to care about all previous orthogonality. We only have to impose this one condition. Then this vector we chose is magically Q orthogonal to all previous vectors. Okay, so we'll prove this next time.